To introduce her briefly, she's a fourth year. I'm sorry, which year are you, Kavya, at PhD?
Yes, it's my fourth year. You got it right.
Advised by Stanford professor Mark Horowitz, and she's going to be talking about this extended GCD, but she's worked with Agile Hardware and the hardware project developing Lake, and has been in a number of publications. Kavya, go ahead and take over.
Sounds great. Thank you. Let me share my screen. All right. Can folks see the PowerPoint?
Yes, we can.
Awesome. And it's full screen?
Yes, it is.
Okay, great. Thank you so much for having me. As Christopher mentioned, my name is Kavya Sreedhar, and I'm a fourth year PhD student at Stanford. Today, I'll be talking about our work on a fast large integer extended GCD algorithm and hardware design for various cryptographic applications. And this is work done with my advisor, Mark Horowitz, as well as Christopher Torn, who is an assistant professor at USC, and also on the call today. So the extended GCD operation is a fundamental operation in number theory and computes Bézier coefficients that satisfy the identity as shown here. This has wide-ranging applications in cryptography, many applications of which we've talked about today, to compute the modular multiplicative inverse for RSA, elliptic curve cryptography, Al-Gamal encryption, and so on and so forth. As a result, a lot of work has been spent on the 80s and 90s to develop fast GCD algorithms, but until recently, there hasn't really been much development in this domain. However, two recent developments suggest that there is a larger need for fast extended GCD implementations. And the first is this realization that constant time XGCD can be faster than Fermat's Little theorem for modular inversion for elliptic curve cryptography, such as curve 25519. The second application is this increased interest in squaring binary quadratic forms over class groups as a verifiable delay function, or VDF. VDFs are useful for consensus protocols. And in fact, Chia, I think there's some folks from Chia on the call here, have been looking into using this particular VDF in their protocol. And for this operation, XGCD is the primary bottleneck, taking about 91% of the execution time when profiled in software. So these two applications have two distinct requirements. For the first, we're interested in constant time 255-bit XGCD because we want to protect against timing side channel attacks. And in the second, we're interested in non-constant time 1024-bit XGCD because the inputs are not secret. And so to work in this space, the first thing we wanted to look at was the prior work that existed. And so to understand that performance, we have these performance plots, and all of our performance plots have clock frequency in gigahertz on the x-axis and the number of cycles or cycle count on the y-axis. And with these axes, we can draw these constant performance lines because the product of cycle count and the time per cycle, which ends up being the inverse of clock frequency, is just equal to execution time. So if I have some clock frequency and some cycle count, I can find another point that's, say, 10 times that frequency and 10 times the cycle count and draw this constant performance. And this means that faster execution time corresponds to points with higher clock frequencies, but lower cycle counts. So better performance corresponds to lines that are closer to the lower right-hand corner, as we see here. So in the 255-bit constant time XGCD space, there are two recent software works. The first is the Bernstein-Yang algorithm from 2019. And there's an FPGA paper that prototypes this algorithm. However, there are no ASIC points to our knowledge in this space. On the 1024-bit side, we see that there are two ASIC points. And in fact, the fastest ASIC is 2 times faster than software. And so what we realized from these graphs really quickly is that not only are there not very many hardware points in this space, the hardware points that do exist focus on using iterative division-based XGCD algorithms and provide point solutions for either constant time or non-constant time execution. And so our goal was to explore the broader design space across three distinct axes: the target platform, software versus hardware, the iterative algorithm operation, and finally, the application requirements. And we find that in contrast to all prior hardware works, it's actually better for performance to use iterative subtraction instead of iterative division. And we further provide a unified hardware unit that is capable of being configured for constant time or non-constant time execution. And this is advantageous because you can do both of these operations with one ASIC, and ASICs tend to be expensive. So our first axis, target platform, software versus hardware. What we recognize here is that the number of iterations are algorithm dependent and platform independent. So this means any lessons we learn in software can be directly carried over to a hardware implementation. But in contrast, the time per iteration or iteration time is not platform independent, because software implementations are inherently constrained to using a processor's ISA, whereas hardware is not. And we have the flexibility in hardware to build custom, fast, wide data paths. And this additional control over iteration time allows us the opportunity to consider accelerating algorithms with simpler operations such as subtraction that might end up taking more iterations compared to division-based algorithms. And that directly leads us into comparing GCD algorithm operations. GCD algorithms are inherently iterative and repeatedly apply a GCD preserving transformation each iteration to reduce your input numbers to finally 0 and the actual GCD. So there are two main families of algorithms. The first is the binary GCD or Stein family of algorithms, which iteratively subtracts the two numbers. Whenever one of the numbers is even, it additionally reduces that number by a factor of 2. So the operations here are shifting or subtracting. On the Euclid side, the iterative operation is division. So the first thing we did was compare the number of iterations for the worst case inputs, which is what we end up using for our constant time implementation. And we actually consider an optimal point within the Stein family of algorithms, which is known as the 2-bit PM algorithm. And this reduces by 2 bits or divides by 4 whenever it's possible, hence the name. And we quickly see that the number of iterations for worst case inputs are quite similar between these two families of algorithms. And given that Stein's / the 2-bit PM algorithm uses subtraction, the operations are much faster, and this is clearly the better family for this application. In the average case, however, it's not quite as simple. We see that there is a 1.6 to 2 times higher cycle count for the 2-bit PM algorithm compared to the Euclid algorithm. So we were interested to see if the time per iteration for the 2-bit PM algorithm would be at least twice as fast compared to Euclid's algorithm, meaning that it would have shorter execution times and thus better performance. And so to actually understand what operations happen and what the iteration times are, we needed to understand what XGCD algorithms are and how we can go from these GCD algorithms to XGCD. And the way we do that, and prior work has typically done, is to introduce these two new relations that are maintained every cycle, with the goal being to solve for these coefficients, which eventually give us the Bézier coefficients we're looking for here. And in order to compare iteration times between 2-bit PM and Euclid, we decide to look at the critical path of operations. So in software, there is typically one data path of operations, but in hardware, you could have multiple concurrent data paths. And the longest data path in hardware is known as the critical path. So we wanted to analytically compare the performance ceilings of the critical paths between the 2-bit PM and Euclid algorithms. So first, the 2-bit PM. The most complicated update in this algorithm is subtracting your 2 input numbers and then dividing by 4. And this corresponds to an XGCD update of subtracting 2 coefficient variables and an additional constant, and then dividing by 4. The details about how this relation is derived and what this update means is in our paper. The important thing to take away from the slide for this talk is just that this operation consists of 2 subtractions and then a shift by 2 or a divide by 4. On the Euclid side, we have to split up our critical path into these 3 parts. First, we need to compute a quotient when we're dividing our 2 numbers. And a fast way to do that is to just approximate the most significant bits of the quotient instead of doing the entire 255-bit or 1024-bit division. And so what we can do is take the most significant bits of our inputs, use a lookup table, which is really the fastest way to do this operation, and then actually output a, for example, 6-bit coefficient that approximates the longer coefficient. Then to actually get the remainder from this result, we need to first multiply the second number, the denominator, by the quotient, and then actually subtract that value from the numerator. And so we can see here that since this multiply is all just multiplied by 1 bit, this really just reduces to taking your number and shifting it some places or just having 0 if you were multiplying by 0. And then we do the subtract and get our remainder. And what we see from these 2 critical paths is that they primarily consist of additions. And so we can use the fastest adder known, which is a carry save adder. And when we typically add, we add our bits and then we propagate carries and go through the bits to get our final answer. In contrast, what a carry save adder does is instead of propagating the carries, it separately stores the carries and stores numbers in this redundant binary form or CSA form with the sum and the carry bits stored separately. And what this means is you actually don't know what the values of your numbers are during your operation, but at the very end, you can add them together to actually get the same result you would expect. So each bit here has a 1-bit full adder, and all of these operations can be done in parallel. So regardless of how long your input bit widths are, there's still a constant delay, and it's independent of bit width. So then we consider what the critical path looks like in terms of this carry save adder delay unit. And we can see for the 2-bit PM algorithm, we now need to subtract 3 numbers. These 2 numbers are in redundant form or carry save form. This number here is just a constant, so we really need to add 5 inputs with carry save adders, which take in 3 inputs and output 2. So this ends up taking 3 carry save adders, and we say that the critical path is 3 carry save adder delays, since a shift in hardware is quite fast. On the Euclid side, we see that first to compute the quotient, we've actually have A and B in this redundant binary form. So to get, say, the 6 most significant bits of these numbers for the lookup table inputs, we need 6-bit carry propagate adds to approximate the most significant bits of our numbers. Then we can do the lookup, which we approximate as 0 for an optimistic estimate. And then we need to actually sum 7 numbers, all of which are in carry save form. So that's really, we have 14 inputs and 3 to 2 carry save adders. And this operation here takes another 6 carry save adder delays. So if we look at this first part, this add took 3 carry save adder delays. The second part took 6 carry save adder delays. And we optimistically estimate that the critical path for Euclid's algorithm requires at least 9 carry save adder delays. So what we see from this is that the 2-bit PM critical path is at least 3 times faster compared to Euclid's critical path. But the 2-bit PM cycle counts were only at most 2 times higher. So this suggests that in contrast to all prior hardware works, it's actually more advantageous to implement the 2-bit PM algorithm in hardware with carry save adders for better performance, both in the average and in the worst case. So finally, if we come back to our last axis, application requirements, for our non-constant time implementation, we do what all GCD algorithms do, which is reduce your inputs until you have the GCD and one of your numbers is 0. For the constant time case, we have a configuration bit that indicates when to do this kind of operation. And we have our algorithm run for the worst case cycle count. So the iterations required for the worst case inputs. And an important thing to note about our work is that since our numbers are in this redundant carry save form, we don't actually know when they became 0. So the algorithm will keep seeing that the number is even and then divide 0 by 2 and 0 by 2 and on and on. So we'll still result in a functional algorithm, even though we run past whenever one of our numbers becomes 0 and we found the GCD. And that way, for any input, we'll always run for the worst case cycle count and end up having a constant time implementation. So this brings us back to the design space, and then we see in the hardware context, it's actually more advantageous to use iterative subtraction instead of iterative division. And we're able to provide this unified configurable ASIC unit for constant time and non-constant time applications. So now that we had found the path in the design space that was optimal, we decided to apply a few more hardware tricks to further refine our point. And we see in our accelerator execution flow, we have a short pre-processing and post-processing step, but the majority of the time is in this iterations loop. So the first thing we needed to ensure was that when shifting in carry save form, we had functional results and that numbers were not incorrectly truncated during shifts and that the sign bit was preserved. The actual circuits of how we did this are in the paper, and we just wanted to highlight this as something to think about. The second thing to note is that the pre-processing and post-processing steps require time-consuming carry propagate adds. And so to ensure we did see the benefit of using these constant delay fast carry save adders, we allocated multiple cycles for these initial steps to ensure those adds did not limit our time. In a related note, we need to determine for the average case when A and B are 0 to know when to end our algorithm. And those again require long carry propagate adds. So we actually compute those over 4 cycles during our iterations. And this means that in the average case, we might add on an extra 3 cycles to our execution time. But given that we are running this algorithm for 400 to 1,600 cycles, this ends up being a very negligible contribution. And then finally, we ensured that we limited the time for generating our control signals, so those did not dominate. And we pre-computed these signals in previous cycles and also duplicated computation and used late selects to ensure these did not limit our critical path. So when we actually look at the critical path for our ASIC in 16 nanometer, we see that it looks like what we'd expect. There are 3 carry save adder delays, and then some time to shift and ensure we have functional results in carry save form. We then have some time for the mux delay to actually select between our options. And then we pre-compute our control signals for the next cycle. And what we see is that with 255-bit inputs in the left column here and 1024-bit inputs in the right column, we achieve very similar cycle times due to our use of carry save adders and carry save form. So because the 1024-bit design is larger, physical design can become a little bit more complicated. And we see that our cycle times are still fairly close to each other when we actually report post-layout numbers for a fabrication-ready, tape-out-ready design. And ultimately, for our 255-bit XGCD, we are able to achieve a frequency of 4.5 gigahertz. And for our 1024-bit XGCD, we can run it at 3.9 gigahertz. And so this suggests that even as we increase the bit width, since we have this constant delay with carry save adders, our clock periods will scale at a similar rate for even higher bit widths. And our work is relatively bit width independent. So now we decided to compare our work to the prior work. And what we see is that our ASIC for 255-bit constant time XGCD is 31 times faster than the fastest software implementation out there. And importantly, it's the first ASIC we're aware of for constant time 255-bit XGCD. So these numbers suggest that it is useful to build custom hardware for this operation. We also compared our work to the Bernstein-Yang FPGA prototype by synthesizing and placing and routing our design on the same FPGA used in that work. And we saw that our design is 45 times faster, showing the benefit of our algorithm on the same hardware platform, on the same FPGA platform. On the 1024-bit side, we saw that our work is 36 times faster than software. and 8 times faster than the state-of-the-art ASIC, acknowledging for technology scaling. So we scaled both their work and our work both down to 16 nanometers for a fair comparison. And again, for the direct FPGA comparison, where we put our design on the same FPGA as prior work, we found that our design is 2.7 times faster. And so what we see aside from the XGCD speedup is that our design has further applications at the application level. First of all, it supports the progression in the state-of-the-art to using extended GCD for modular inversion for curve 25519. And it suggests that it's worth re-examining what the bottlenecks are now in point multiplication algorithms that were previously significantly dominated by inversions. The second benefit is that since we saw that we had a 36 times speed up from software, it informs what reasonable security levels need to look like for this PDF and how long our bit widths need to be to ensure a certain level of security. And we've actually seen a new paper build upon our work and consider accelerating this full VDF. And we've been talking with Chia as well to understand their implementation of this algorithm and how this all might work together. Finally, this may be useful for other applications, and we really are interested in learning about other applications that might rely on XGCD and how we might be able to apply this work to that. So if there's anything you have in mind or anything that you think would be interesting, we really would love to hear about it and chat more. Finally, like Christopher mentioned, all our work is open source and available at this GitHub. In the spirit of the second talk, we actually do have scripts for the OpenPDK Sky 130 for our design as well, which has similar speed up numbers, but with a 130 nanometer level instead of the 16 nanometer presented today. So if you're interested in that, we can also talk further about that, and we'd be happy to take any questions. Thank you.
Thank you very, very much. I have a couple of questions. Now, you say that obviously curve 25519 is evolving, has some issues with aggregatable multi-sig, and so they've been moving to Ristretto. I think from what I understand, there's no limits. You can support the 2559 equivalent in Ristretto, correct? Or does that require some change in your code?
As long as, so ours is focusing on the GCD. So as long as the GCD part of it, extended GCD part of it is still just required for modular inversion, as long as modular inversion is still in operation, it's a plug and play. The actual application is not, it doesn't depend on that. And that's true for different bit widths as well. We'd been using curve 25519 just because it seemed like something the community was recently interested in. But if there are other bit widths and other curves that are more valuable, it's a matter of changing a parameter in our generator.
What about things like SECP and such? Any generalizations, thoughts?
Can you, maybe I'm not familiar with that. Could you explain that a little bit further?
Well, we can do that more in the SECP is
Sure.
256K1 is what Bitcoin uses, and R1 is what is the NIST standard. I just wondered if you had looked at either of those.
Yeah, we've really been focused on the XGCD just because this had seemed to be the bottleneck. But if there are other applications that would be interesting or that are complementary to this, we'd be happy to take a look.
Okay. Other questions?
Yes, I have a question. Could you by any chance shed some light on like which group at Stanford you're doing this work with, and what else the group focuses on?
Definitely. So my advisor is Mark Horowitz, and he works on VLSI and computer architecture and chip design broadly. So he has both the digital subgroup as well as an analog group. And within that, so Chris on the call as well, different Chris on the call as well. And I have really been the main folks looking at hardware for cryptography applications in our group. And we've been working with Dan Benet as well, who's been advising us on interesting applications to look at and things that might be interesting for us to accelerate. So he steered us in the direction of VDFs. And then when we profiled it, it became pretty clear that XGCD was really the bottleneck. And we became interested in trying to find other interesting applications for this work and what the community was looking at. So really, it's a relatively new effort from the hardware and cryptography space, but Dan has been working in cryptography for a very long time, and Mark has been working in hardware for a very long time. So it's really a marriage of those efforts.
That's very interesting. Thank you.
There's one other angle here. So in the group that so I just came from Stanford, by the way. So I'm in my second week at USC. So the group that we're in is the Agile Hardware group, right? And so we're kind of a more methodology focused and very, very open source hardware team. And so we build hardware in a way that we can kind of automate the software and the hardware as they're working together in this with respect to domain-specific hardware accelerators. And we basically put all of our code and our tools that we develop online on GitHub. And so if you go on and you search for Stanford AHA, you'll see a collection of all of our tools, Lake being one of them that was in Kavya's biography. So I think that this connects a little bit with the second talk, because free and open source software, free and open source hardware, I think there's a lot of things we can talk about later on in the discussion section, but that's the kind of context that we're coming from.
Are there any other organizations and groups? I mean, for me, this is exactly the type of stuff that, we need to introduce to the silicon designers, down the stack, and the software designers up the stack. But there's actually not a lot of this type of work that I've been able to identify. Are there any other particular, either within your own group, candidates for another item to accelerate, or in other groups that you've admired their work?
I think there's been a huge push towards open source in our group and at Stanford in general. I think for the cryptography application, it is more of a newer thing that has been introduced to the group, but I see it growing, I think, in future years.
Yeah, so I think that there's kind of maybe two parts, right? There's like an interest in crypto security and hardware, and then there's a separate interest, which is more about open source hardware. And those two don't necessarily overlap. They happen to overlap for us because we got interested in crypto by talking to Dan, and then we are coming from the background where we care a lot about methodologies and open source hardware. Off the top of my head, since it's the top of my head, they might exist, but off the top of my head, I can't think of any right now where those two overlap really well. But just keep in mind that if you're working on hardware accelerators, the amount of work that goes into these is significant, as you can probably tell from this talk. And if you want things to go really fast, then you usually aim for the best, most advanced technology. So we implemented this into TSMC 16, also a similar, so basically that, advanced technology. But as Bunny mentioned, if you go to the open source PDKs and flows and the standard cells there, they are much, much worse than certainly much worse than advanced technologies, but even worse than that at this moment of maturity of open source hardware and open source physical design. The libraries that are actually released for 130 are worse than the commercial libraries for 130 from the past. And so for this particular application, we care a lot about performance. And if you go back to an older technology and you try to build the same design, you end up trading off a lot of performance, and it kind of doesn't really capture the research goals of trying to pull out which techniques actually made a difference, right? And then you have to add these caveats for why the technology is not exactly right. And so the groups that want to overlap open source hardware with maybe getting really good performance in a particular application, they need to ride this delicate trade-off thing. And that's not something that's easy to do. You kind of need to do both. And we actually did both, which is probably why we caught Christopher's eye.
And
well.
Some rough numbers just to add to Chris's point. So we had 3.9 to 4.5 gigahertz in 16 nanometer. And in Sky 130, which is a completely open PDK, we were around 300 to 500 megahertz, if I remember correctly. So it's significant difference, which is to be expected from the older technology node. But I think that also doesn't capture the designer effort that went into bringing up Sky 130, which I think was clear from Bunny's talk as well. But it did take a significant overhead to get the PDK working. And even with the open source tools, we just found out that this design was a bit too large to actually have synthesis or place and route even complete. And so we had to end up using commercial tools because our runs were running for days without signs of finishing. So it's kind of this trade-off, because we really want to do our best to make this work as open and freely reproducible and accessible as possible, which is why we're trying to post this online and using the Sky 130 PDK, but there are inherent challenges with using open source tools as well. Yeah.
Great. Well, thank you very